Welcome back to the Future of Flight. In this video, we will be discussing propulsion techniques and innovations about propulsion. We will start with turbofan engines and then also look at electric propulsion. So let's go to the article directly. Propulsion systems. So here is the link. So in this third article in the series, this is a report published in May 2019 by The Economist magazine about the future of flight. So what can we expect in the propulsion technologies? Here we see a schematic diagram of a turbofan engine. In addition, there is a really advanced gearbox in the system, which decouples the speed of the fan and the rest of the mechanism. That we are going to learn in this article why this is interesting and why an already complicated system has added a gearbox on top of it. Okay, the article's title says smaller planes could soon use electric propulsion and turbofans for larger craft are improving rapidly. So we have a revolution for smaller planes. It is possible to electrify smaller planes soon. And then we have evolution of turbofans for larger craft. The first part of the article is about the turbofans. We will look at electric propulsion in the next video. So the article opens with a bit of history of jet engines, and then the opening sentence is even interesting or shocking or surprising, saying that it says jet airliners are not in fact jet airliners. We will in a moment understand more what this statement is really about. So the author is looking at the history of jet engines. He brings us one of the first jet airliners, the English de Havilland Comet, which was really so this aircraft really was powered only by sleek turbojets that fitted elegantly into its wings. Before continuing this sentence, I would like to show you this de Havilland Comet. Here is the aircraft we are talking about from early 1960s. Basically, what we see is two sucking pipes. So these two are the jet engines. So this is what the article says, sleek jet engines mounted on the wings. It looks certainly different to today's jet engines. So in this one, we basically have the combustion sucking pipe, the combustion chamber, compressor, but we don't have a fan in front. All the air sucked goes through this tube and creates a thrust. So this is the most basic jet engine. Today's jet airliners are not, of course, using this type of engine. And the article is making that point. Okay, coming back. Let me read from the beginning. Though the first of the breed, the de Havilland Comet really was powered only by sleek turbojets that fitted elegantly into its wings, and we just saw that it is the jet engines really are elegantly fit into the wings, almost invisible. But it did not take engineers long to work out that a turbojet works best not by itself but as part of a bigger whole. So I would like to show you more current jet uh, systems that have the jet engine part of it. So here is one. This type of, if you, here is the sucking uh, tube here. So we have a propeller. So this type of a jet engine is called a turboprop because of this propeller. So the propeller helps air, helps the sucking of air, and this increases efficiency. And for really small aircraft, turboprops are used. And for jet airliners today, we have we have a duct here, a pipe, and a fan in front of the pipe that sucks the air. And not all of the air goes through the engine, but some actually most of the air sucked is bypass the engine and go around the engine. Actually, the amount of air going around the engine compared to the air going into the engine, into the combustion chamber, is called the bypass ratio, and that is a measure of the efficiency of turbofan engines, which we will learn in a moment. Okay, coming back to the from turbojets to turboprops and turbofans. Okay, now let's have a look at these three types of engines. The basic idea of a turbojet is that it takes in air through a revolving compressor, mixes the compressed air with fuel, burns the mixture in a combustion chamber, and ejects the exhaust out of the back to provide thrust. But before exhausting, we also have a turbine there that is connected to the compressor. So if I must show you the picture once again, here is we suck the air here. First it goes through a compressor, then the combustion chamber, and before the exhaust going out, there is a turbine here. The turbine helps run the compressor because they are connected on the same shaft. So this is the basic turbojet mechanism. Modern engines, however, also use the jet's revolving shaft to spin either a propeller, creating a turboprop, or a ducted set of blades, creating a turbofan. So basically, a propeller is connected to the shaft to suck air more efficiently. That is a turboprop. Or if we have a fan, blades, and the engine and the blades are inside a pipe like structure, a duct, that is a turbofan. That is the essence of a turbofan engine. Both these arrangements, and particularly turbofans, move more air and thus create more thrust than the turbojet, which is capable of generating by itself. So both of these arrangements, particularly turbofans, move more air and thus create more thrust than the turbojet within is capable of generating but it's by itself. So this extra system, especially the duct and the fan system, gives the turbojet engine extra efficiency. For long-haul flight, therefore, turbofans are preferred. Okay, having looked at the basics of turbofan jet engines, now let's look at which companies are in this business. I will continue reading. As with making large aircraft themselves, the business of building turbofans is confined to a few big firms. I think this is not surprising. According to Market Research Future, a consultancy, General Electric, GE, and United Technologies, trading under the Pratt Whitney brand in America, Rolls-Royce in Britain, and CFM International, a collaboration between GE and Safran of France, account collectively for almost 93% of the turbofan market, and each is intent on upping what is known as the bypass ratio of its engines. So let me switch to my presentation. Okay, and then make a summary of the companies. So the bulk of the turbofan market, 93%, is two companies from the United States, General Electric and United Technologies. They're Pratt and Whitney engines. Britain has Rolls-Royce, and CFM International is a collaboration between GE, General Electric, and Safran, which is a French company. Okay, so this is the landscape. Let's go back now to the article once again. Okay, now the last sentence here says, and each of these companies is intent on trying to do upping what is known as the bypass ratio of its engines. So each of these companies are busy trying to increase their bypass ratios. Let's have a look at this bypass ratio in detail. A turbofan's bypass ratio is the amount of fan-driven air it expels from the rear divided by the amount of exhaust from the combustion chamber. So it's the ratio between the fan-driven air coming out from the rear and divided by the amount of exhaust from the combustion chamber. So these ratios are typically 10 to 1. This shows that the combustion chamber is only outputting 1, while the ducts are actually sending about 10 times more air. The bigger the bypass ratio, the more efficient the engine. More efficiency means lower costs. It also means less environmental impact. Okay, so having understood bypass ratio, let's have a look at some real values. The GE 9X, as fitted to Boeing's new 777-9X aircraft, which was rolled out on March 13th, 2019, shortly after the second of the 737 MAX crashes, by the way, is currently the world's largest turbofan. I will show a picture of this. It has a bypass ratio of 10 to 1. So here is Boeing 777-9X, and this is the GE9X turbofan engine, bypass ratio 10:1. Next, we will read the Rolls-Royce Trent 7000, also 10:1 bypass ratio. This one is Airbus A330. So these are large aircraft. On the smaller ones, we will see CFM's LEAP engine having a 11:1 bypass ratio, and Pratt Whitney's PW1000G 12:1 bypass ratio. So we can say this one is more efficient compared to that one, uh, uh, the CFM LEAP, which both of which are more efficient than the 10:1 engines. But again, these are for smaller aircraft. This is A320, and I think that's a Boeing 737. So let's come back to the presentation. So we learned about GE's 9X. The latest iteration of Rolls-Royce Trent, the 7000 we just saw, will also have a 10:1 ratio. And CFM, which specializes in engines for narrow-bodied jets and thus avoids treading on GE's toes, basically because they are collaborators in the wide-bodied jet market, has an engine called LEAP with a bypass ratio of 11:1. The daddy of the field at the moment, though, is Pratt and Whitney's PW1000G, branded Pure Power. Its best performing version has a bypass ratio of more than 12:1. Okay, so we have an idea of typical bypass ratios and the companies that are trying to make their engines more efficient by making the bypass ratio larger. So what is stopping them than making these ratios even larger? We will learn a little more about this here. Okay, let's have a look at how Pratt and Whitney achieved 12:1 ratio. And this is the result of a gamble. Turbofans are complicated beasts put together from about 25,000 component parts, already complicated. The company's engineers decided to make them more complicated still by adding a gearbox. The gearbox reduces the speed at which the fan blades spin relative to the shaft. You want the shaft to spin rapidly because it drives the compressor, but that high rate of revolution puts a strain on the fan blades. Reducing this strain allows the blades to be longer. This is of course due to the centrifugal acceleration, meaning the engine can have a wider air intake that is able to gulp in more air and thus to achieve a bigger bypass ratio. The point of studying the article in detail is we now have a look at what is happening in these top companies producing jet engines. And I actually put two videos on our presentation file. You can learn more about the Pratt and Whitney's Pure Power engine. I've got two videos which are available on our presentation. Okay, so coming back, we looked at gearing, but the article continues. Gearing is not, though, the only way to make engines more efficient. Better materials also help. As with air frames, replacing metal alloys with composites saves weight, which saves fuel, and composites also offer a way to deal with an engine's intense heat. Okay. So the heat and mechanical stress is making the selection of materials crucial for the efficiency in a jet engine. So let's learn more about this. Two composite materials are particularly pertinent to aircraft engines. For fan blades, carbon fiber reinforced plastics, similar to those used in airframes. And for components that need to be heat resistant, ceramic matrix composites, in which both the fibers and the matrix are made of a material such as silicon carbide. Remember, the resins were polymers for the uh, carbon fiber reinforced plastics. At the moment, GE leads the way in the use of these materials in engines. So GE leads the way in the use of these novel materials in engines. It has been making carbon fiber blades for its turbofans since the 1990s. In the case of LEAP, this halves the number of blades required. Remember, LEAP was produced by GE and Safran for narrow-bodied jets. In the case of LEAP, this halves the number of blades required. So using carbon fiber reinforced plastics halves the number of blades required compared with its predecessor, the CFM 56, from 36 to 18. So the number of blades are halved, making it, of course, more easy to produce, making it simpler. GE also makes extensive use of additive manufacturing, commonly known as 3D printing, which permits the manufacture of shapes, including weight-saving voids, empty spaces inside, that conventional manufacturing can manage only with difficulty, if at all possible. So this is what is happening on the GE side. Rolls-Royce, meanwhile, is planning to go the whole hog using a gearbox, carbon fiber blades, and a range of ceramic metric composites in what it calls its ultrafan technology. So Rolls-Royce is trying to use everything to create the best possible turbofan engine, which it hopes will permit bypass ratios above 15. So above 15. Ultrafan will also make use of additive manufacturing, and naturally every component in an ultrafan engine will have its digital twin in Rolls-Royce computers, keeping track of what is happening to it and flagging up any maintenance-related issues. So it looks like they are bringing everything together. A gearbox, carbon fiber blades, ceramic matrix composites, and additive manufacturing. They want and the digital twin. Now, while we are reading the article, it might seem like you are not really moving forward, but it's if you be patient and finish this series of videos, you will be surprised to see how much more current information you actually learned. And the thing is, they are also connected. We learned about digital twins in the manufacturing part, and now we see Rolls-Royce using digital twins. Now that idea comes in here as well. Okay, so this is all we have for the turbofan engines. Let's look at the presentation also. So I wanted to summarize carbon fiber reinforced polymers for fan blades, ceramic matrix composites for heat-resistant components, and then additive manufacturing is being used as well. Okay, this is all for the turbofan engines. Next, we will have a look at electric propulsion for smaller planes. Thank you.